Okay, so today we started our journey into particle physics. This will comprise the last two lectures of the course. We started off by looking using PowerPoint at the idea of the standard model, which explains all of the particles we see through the combination of the fundamental forces, the leptons and the quarks. From here we've gone on and really started to look in detail, and the first thing we talked about was the equivalence between mass and energy. And we showed that we can write mass in units which allow us to switch easily between mass and energy. So instead of writing mass in kilograms, we write the mass of many particles in units of MeV, mega electron volts, divided by c squared. As I said to you, if you remember, often people forget to put that c squared bit in. So if you see a mass given in MeV, what they mean is MeV divided by c squared. Okay, we then started to look at how we classify particles, and we looked at familiar and unfamiliar properties of particles. So familiar properties are things like the charge and the mass. More unfamiliar properties, we started by looking at the spin, which deals with the intrinsic angular momentum of the particles, and we showed that each particle has a spin quantum number associated with it. That spin quantum number broadly falls into two families. Particles where the spin quantum number is an integer, and these particles are called bosons. So there the spin quantum number could be 0, 1, 2, 3. And particles where the spin quantum number is a half integer. So it could be a half, 3 over 2, 5 over 2. And these particles are called fermions. And we see that bosons and fermions have quite different behaviour. So for instance, fermions obey the Pauli exclusion principle, whereas bosons don't. We then went further and came up with some more definitions of particles, and we saw particles that experience the strong force are called hadrons, whereas particles that don't are called leptons. Okay, interestingly, hadrons means the heavy ones, leptons means the light ones. We then went further and saw that we could have hadrons that were also bosons. So hadrons being particles that experience a strong force, bosons being particles with integer spin, and we saw that those are called mesons. And okay, an example of meson would be a pion, for instance. And we saw that we can have hadrons that are also fermions. So particles that experience the strong force that are also fermions. And the ones you're most used to here are probably things like protons and neutrons. Next we looked at antiparticles. We saw that Fermi predicted some time ago that a particle can have its antimatter equivalent. The antimatter equivalent has the same mass and the same spin, but the opposite sign of charge. So for example, the electron has a sibling particle called the positron, which has a positive charge. By convention, when we write a particle, when we write the antiparticle, we write the particle symbol with a bar on top. So for instance, if we have nu, which is a neutrino, we write the antineutrino nu bar, again with the bar on top. I think I forgot to mention this during the lecture. We then went on and saw how we could experiment with particles, and I showed you a couple of slides of particle accelerators, so for instance CERN or SLAC at Stanford, where particles are accelerated to very high speeds, and then we had collisions going on which allowed us to see many new particles being formed. Finally, we looked at how we can understand particle interactions and particle decays, and saw that to understand these we have to make use of conservation laws. To start with, we looked at using conservation of energy, both in terms of the kinetic energy and the mass. We looked at conservation of charge, we looked at conservation of spin. We also showed that conservation of linear momentum can help, particularly when analysing things like bubble tracks. We looked at, in this case, at beta decay, and saw that beta decay satisfies all of these, so conservation of energy, charge, spin. We then saw that as well as those things, we also have to conserve, for instance, other quantum numbers. So here we introduce this idea of baryon number, where for baryons, the baryon number is +1. For antibaryons, it's -1. For all other particles, it's 0. This too has to be conserved, which means that, for instance, the decay of a proton to a positron plus a photon, where a photon is illustrated with a gamma sign, which again I forgot to mention during lectures, we saw that can't happen because in this case baryon number isn't conserved. Similarly, we can have a similar thing for leptons. So for a lepton we have +1, for an antilepton we have -1, and for all other non-leptons we have 0. That's the lepton number, and again that also has to be conserved. Finally, we came on and looked at a final quantum number, which was the strangeness of a particle, which is an intrinsic property of the particle, just like anything else. And we saw that again, strangeness has to be conserved. What we find is that strangeness occurs in particles that experience the strong force, and it must be conserved when the strong force is used. And so we can define, as I say, the strangeness quantum number. Much more on this next time, when I'll talk to you about the eightfold way and how we can use this kind of idea of strangeness to begin to predict new particles. So I hope it wasn't too confusing. All the terms are quite confusing, so what I would recommend really is that you spend a little while looking through the lecture notes, and if you've got any questions, please come and find me and ask me them. And I'll see you all on Monday.